Welcome to The Explainer. Today, we're diving into a genuinely fascinating challenge that connects two worlds you might not normally put together: the hyper-realistic graphics of modern video games and the life-saving technology behind autonomous cars. At the heart of both fields lies one massive computational hurdle. We're talking about temporal motion tracking, specifically the incredibly complex challenge of tracking pixel movement across time.
So, how exactly does a computer know where a single pixel is moving from one frame to the next? It sounds like a super simple proposition, right? Well, it turns out answering this one question is the absolute secret sauce. It's the underlying math that unites how a virtual game world renders a running astronaut and how an automotive stereo camera calculates the exact trajectory of a turning vehicle.
Here's our roadmap for today. We're going to start with the pixel motion problem in virtual environments, look at how developers erase virtual ghosts, then jump over to tracking real-world motion, and finally, unpack the sheer power of an algorithm called dense 6D. Let's get right into it. Okay, Section 1, the pixel motion problem and how it impacts rendering virtual worlds. If you want to render a truly beautiful virtual world, game engines have to tackle those ugly, jagged, pixelated edges. Unreal Engine 4 handles this by default using something called temporal anti-aliasing, or TAA for short. Now, instead of just analyzing a single isolated frame, TAA compares multiple frames over time and blends them together. It does an amazing job taking scattered, dotted edges and turning them into incredibly smooth, solid lines.
But, as with everything in computer science, there's always a trade-off. TAA is absolutely fantastic for static scenes. It gives us gorgeous screen space reflections and perfectly smooth edges. But the second things start moving, that's where we run into trouble. If an object, say an astronaut manipulated by a vertex shader, moves across the screen, blending all those past frames together inherently creates this blurry, ghosting effect. The engine is literally dragging a trail of past pixels behind the moving object.
Which brings us to Section 2. Erasing virtual ghosts. So how do game engine developers mathematically solve this ghosting artifact?
Well, to fix this in Unreal Engine 4, developers basically have to force the engine to calculate exactly where those pixels are going. You go into the project settings, down to optimizations, and check output velocities due to vertex deformations. Now, doing this definitely comes with a heavy performance cost, and you have to recompile all your shaders, but the mathematical result is absolutely vital.
By flipping that switch, you create what's known as a velocity buffer. It's a total game changer. The virtual world now knows exactly where an object is heading on a pixel-by-pixel basis, because the game engine itself is dictating the underlying mathematical velocity. Armed with that exact data, the engine can perfectly reverse the ghosting blend during post-processing. The computer knows the motion simply because it generated the motion.
But here is the ultimate pivot, right? Think about it if tracking pixels is mathematically heavy in a video game, a controlled environment where we literally own the source code and generate every movement. How on earth do we pull it off in the messy reality of the physical world? Out here, a camera only sees flat, raw pixels. There's no underlying engine code to tap into that says, hey, this cluster of gray pixels, yeah, that's a car moving at 30 miles per hour.
That leads us right into Section 3, tracking real-world motion using stereo image sequences. Let's see how Daimler's automotive vision research tackles this exact problem out on real roads. This is a brilliant illustration of the real-world challenge we're facing. On one side, we've got a standard, flat, grayscale traffic camera feed. On the other, the goal, what the computer actually needs to see. It needs a precise 3D color-coded velocity map, where, say, green means stationary and red means something is moving fast. Extracting that kind of rich, dynamic motion data from flat images is incredibly difficult.
The researchers point out some pretty massive hurdles here. First off, just trying to match similar pixel brightness from one frame to the next, it's what they call an ill-posed problem. Basically, there isn't enough info, and there are way too many wrong answers. Secondly, cameras produce naturally noisy depth measurements, which directly leads to noisy motion estimation. And finally, for an autonomous car, this calculation can't take seconds to run. It needs robust, dense information pumped out in real time, at least 25 frames per second. Because when we're talking about safety, absolute accuracy is non-negotiable. So how do we actually solve it? Section 4, the power of dense 6D, merging vision and math. Let's look at how researchers managed to reconstruct these robust motion fields in real time.
The dense 6D process breaks down into 3 heavy-hitting steps. First, it uses stereo matching to figure out depth using semi-global matching. Next, optical flow calculates the 2D pixel motion between consecutive frames. But the real magic? That happens in step 3, Kalman filtering. Assigning a complex Kalman filter to every single pixel in real time to continuously integrate its motion over time is just a massive, incredibly impressive feat of modern GPU power.
Now, looking at the underlying error distributions for dense optical flow and stereo disparity, you can see exactly why raw camera data is so tricky. It is incredibly noisy. What the Kalman filter does is take that noisy positional data and dynamically smooths it out over time. It constantly predicts where the pixel is going and then corrects itself with every single new frame. It's essentially building that velocity buffer we talked about earlier in video games, but reverse engineering it straight from reality. And the results? Honestly, they are staggering. Take a look at these root mean square, or RMS errors for different methods. Direct optical flow gives you a massive x-velocity error of around 42 meters per second. Obviously, guessing a car speed with a 90 mile/hour margin of error is a total non-starter for self-driving car. But look at the bottom two. Dense 6D and variational 6D drop that error all the way down to just 0.36 meters per second. They vastly outperform direct methods by successfully minimizing errors through heavy spatial and temporal regularization.
Now, you might be looking at this and thinking, well, variational 6D is also highly accurate, right? True. But for future tasks, researchers are betting on dense 6D. The reason is simple. It relies on a much less complex computation scheme. When you're trying to run these safety systems in real time at 25 Hz on FPGAs and GPUs strapped inside a moving car, computational efficiency is the ultimate tiebreaker. Dense 6D maintains that massive accuracy while actually being fast enough to use.
When you combine all these techniques, the output is just incredible. The system isn't just seeing cars in a 3D grid, it's actively generating real-time predicted motion vectors. It is plotting exactly where crossing vehicles will be a full quarter of a second from now. The computer has, for all intents and purposes, successfully reverse-engineered the velocity of the real world.
Let's wrap this up by emphasizing why this absolutely matters. Dense 6D isn't just theory. It operates highly accurately in incredibly chaotic real-world traffic scenarios. It easily handles complex tracking, like juggling multiple pedestrians crossing the street while other vehicles are turning. It even compensates for the motion of its own camera. This dense, robust motion field estimation is quite literally the foundational math that will power the safety of autonomous vehicles and advanced driver assistance systems for years to come. It's genuinely amazing to think about. Whether you're trying to erase ghosting artifacts off a virtual astronaut in Unreal Engine, or predicting a turning car's trajectory to prevent a real-world collision, you are dealing with the exact same fundamental puzzle. As virtual rendering and real-world vision continue to converge thanks to advanced algorithms and massive leaps in GPU power, it really makes you wonder, what will computers see next? I'll leave you to ponder that. Thank you so much for joining me on this explainer, and as always, keep learning.